Hello and welcome! In response to my last video, many of you raised thoughtful questions about the real-world profitability of triangular arbitrage. And that's exactly the kind of critical thinking this topic deserves. It shows we are focused on substance, not just surface-level results. So in this follow-up we are going deeper and more practical. We'll build a Python script that scans every possible triangle across Binance, filters for real liquidity, pulls live order books in parallel, and simulates the actual trades, fully accounting for fees. This one, quite frankly, is not beginner friendly. We are diving into real execution logic with full data coverage and zero shortcuts. If you're serious about testing whether this works in live markets, stick around. Every line of code matters. Let's see if triangular arbitrage holds up under real market conditions. Alright, let's fasten our seatbelts, take a deep breath and go through it together step by step. Starting with the libraries. We need sysexit to stop the script immediately if no arbitrage cycles are found. Time provides us the sleep function. We're using that to briefly pause between API calls to avoid exceeding Binance rate limits. Thread pool executor and as completed from concurrent futures enables us to critically improve the performance of the script. Background here is, imagine you're pulling hundreds of order books. Now, if you would do that sequentially, meaning you pull one order book, then the next one, then the next one, then the next one, and so on, this would take a lot of time. Using multi-threading here, you can just pull a big number of order books at once. So this is purely for performance here. Pandas, nothing new here, just data handling, and the client from the Python Binance library to pull market data such as order books and liquidity measurements and many more functionalities, which we will go through in the next few minutes. Then we get to the parameter setup here, starting with the fee. I'm taking 0.1% here on each trade. Now, we will apply that on all three legs to get realistic net profit. So, if you are doing a triangular arbitrage strategy, you have to keep in mind you have 3 trades, so you have to pay 3 times 0.1% for each trade. Then I'm setting an order book limit. This just fetches only the top 5 bid and ask price levels from each order book. That's simply also for performance reasons. Now, volume limit. We ignore any trading pair whose 24-hour quote volume is under 10 million, ensuring our markets are just liquid markets. Then I'm setting a list here containing stablecoins. These assets anchor every cycle start and end in a dollar-pegged coin to measure profit in stable units. Also, I'm limiting the amount of possibilities. You can play triangular arbitrage also on non-stablecoin related pairs, but my assumption here is you start at a stablecoin and you end in a stablecoin. This is the number of threads, so the ones we're using to fetch order books concurrently. And I'm using 10 because it's fast, yet respectful of API limits. This delay sets a waiting time for every thread. So every thread waits 60 milliseconds after its request to stay under Binance rate limit. And top N is simply the 5 most profitable cycles to keep the output concise. So this is the parameter setup. So let's move on to the first coding block, which ends here. So what exactly does this do? First of all, client get ticker requests 24-hour statistic for every market, including the quote volume. This dictionary stats map just sets a symbol and a quoted volume. So you just have symbol, for instance, BTC USDT, and a quote volume for the last 24 hours as a float. Nothing more than that. Then you pull exchange info, and this retrieves metadata for all markets, including their trading status. And then you filter this. So you filter this info for only actively traded symbols. So you check for the status, is it trading, to get rid of all non-traded pairs here, because you simply cannot include them in your analysis as you cannot trade them. And you also apply the minimum volume filter here. So you are accessing the stats map containing all the 24-hour quote volumes, and you filter those symbols which are below the threshold. So you only keep those symbols which are above 10 million trading volume. Nothing more than that. In the end, you're getting a feedback here. You are considering X trading pairs with volume over 10 million. That's the first block. So with that, you have a list of symbols with which are trading and which are above the volume limit. First step done. Very good. Next step, and this is only this coding part here. So this builds up a lookup map for direct and reverse trading path. So you initialize an empty dictionary, pair map, this one here, and then you loop over each filtered market S in the symbols. So filtered, I mean by the trading and volume filter. And then you set BQSim is the base asset, that is the asset you sell to get the quote. The quote asset, that is the asset you receive when selling the base. And you have the symbol, that's just the market string. So for instance, BTC, USDT, ETH, USDT, and so on. And then you set a key to BQ or QB. BQ means, so you set this to the symbol and a boolean, and BQ means to go B to Q, use market sim, so use this symbol and treat it as a cell of B. When we simulate this, we will take the best bid price from the order book. That's why you're taking the B here. Example, you have ETH, USDT. This is a symbol of ETH, USDT as a full string. And true, that means you're selling ETH for USDT. Then you have the reverse mapping with the key QB. This sets a symbol and then false. And that means you go from Q to B. So you use the same market symbol and treat it as a buy of B. In the simulation, we'll take the best ask price. Example, USDT, ETH. Now, that is as a full string, ETH, USDT still. But the boolean is false. That means you are buying ETH with USDT. So just to make it clear why this matter. We have a single dictionary that, given any two currencies, A and B, so in our example, USDT and ETH, tells us exactly which Binance market symbol to query and whether we are selling A, so we are taking bids, or buying A, so we are taking ask. This flat lookup completely removes complex nested conditionals later and makes our simulation codes concise and error-free. So again, you have two keys here, BQ and QB. One is for going from B to Q, this one, and one is from going from Q to B. Just to make this really clear and go over the example again. In this case, so in the upper one where you have a true boolean, you have ETH USDT, and you set it to true, means you're selling ETH for USDT. And in the below, when the boolean is false, you are buying ETH with USDT. Next up, the construction of all possible stablecoin-based triangular cycles. So, what are we doing? First, we are constructing a set. That's what this coin's variable is holding. And that contains every currency appearing as the first element in pair map keys, excluding the stablecoins. So this is a simple filter if C not in stablecoins. These are the intermediate coins we'll cycle through. Then I'm using a list comprehension here to build the triangles. I is looping over each stablecoin anchor. J and K loop over the coins, skipping pairs where J is K. So if J is not K, and then you include I, J, K, only if all three legs, I to J, J to K, and K to I exist in the pair map. And with that, you are getting exactly how many candidate triangular roots you will simulate. And this is what I'm also printing out here. Why is this necessary, or why are we doing this at all? This exhaustively lists every valid stablecoin to coin 1, to coin 2, to back to the stablecoin path, ensuring you test every potential arbitrage cycle. And then finally, so you have everything, right? You have your triangular roots, you have your symbols, you have to have the direction, so you want to sell or buy, which I explained above here. Then you have the triangular roots. Now you need the market data, so the order book data. And this is what this whole code block is about. So unfortunately, I'm just putting that a bit lower here, but we have to scroll, but let's move through it together step by step here. So with symbols to fetch, that's super straightforward. So first of all, you collect symbols for each triangle ij, k. You get the market symbol by simply indexing for the first element for each. So ij, first element, jk, first element, ki, first element. And then you combine these into a set to remove duplicates and then sort it into the symbols to fetch. With that, you're just getting the unique order book calls you have to make. Now, this is also printing out how many order books you're fetching. And after you have filtered, removing duplicates, and you have all the symbols you need to pull via the API or via using the multi-threading logic in the next step, you first define an helper function, which is fetch. And this helper function just calls the getOrderBook function from the Binance client or the Python Binance client to get the top 5 bits in us. So you just set the order book limit. Just a recall, this was set to 5 in the beginning. And then you set a sleep timer here just to avoid rate limit bans. In the end, you return sim and the order book if successful, or sim and none if any exception occurs, so you're not pulling the order book for whatsoever reason. After you've defined the helper function, you are ready for the parallel execution part. So this is happening here. So you set a order book dictionary and you fill it using the thread pool executor. So you set the max workers to the defined 10 in the beginning, and then with that you submit the helper function fetch to get the order book, and you're doing that for all the symbols to fetch without duplicates. And then in the end, if that is completed, you process that for each finished symbol as soon as it completes, so you don't wait for any slow requests. In the end, you just store it in the order book dictionary. So you just, for a symbol, store whatever the results of this thread is. In the end, you just print how many order books you fetched, ensuring the simulation has the data it needs. Good. Now next part. So you have all order books pulled for all the symbols which you have filtered for all the triangular path. And finally, you're just simulating those triangular cycle and also calculate the profit. So you have all data now, you have all path now, and now you need to simulate the whole cycle. So buy, sell, buy, and so on. Now, this is just populating a list here, results, and then it's moving through the triangles defined above, starting with an initial amount. So you just start with 1 unit of the stablecoin, and then you go through the 3 trade legs. That is I to J, J to K, and K to I. This is simply the triangular path. And then for each leg, you look up the symbol and the direction from your pair map, and then you retrieve the order book, and if it's just missing, you exit or you skip, and if it is there, you define or you determine the price, and this is dependent on the direction. So if you are, or if selling is true, then you use the order book's bids, so the highest bid in this case. So you just screen for the first element, meaning the highest bid. And if selling is false, you use the ask prices, so the lowest ask in this case. That is your price. So again, if selling is true, you see direct is the variable can be true or false. And if that is true, you're taking the highest bid. If that's false, you're taking the lowest ask. Super simple. And then simply you calculate the amount logic. So simply you take the amount, multiply it with the price, multiply it with 1 minus fee in case you sell. So if direct is true, you sell. If direct is false, you buy. And then it's this one. So if you buy, you take your amount divided by the price times 1 minus the fee. And if you're selling, you just have an amount times the price times 1 minus the fee. Now, if amount is not none, that means if amount is still defined, you compute the profit. And the profit, and you just also store the cycle, so you get exactly what profit this relates to. So you just define I, first asset, second asset, third asset, the initial asset. So just to make this more understandable, you start at stablecoin, USDT, you buy some Bitcoin, you transfer it to Ethereum, and then you transfer it back to the stablecoin USDT. Again, this is what this cycle is about. And then you just calculate the profit in percentage by taking the final amount minus 1 times 100 to get it in percentage. So with that, you're getting, for each cycle, you're getting a profit percentage. Now finally, this is super simple. If you don't have any results here, then there are no arbitrage cycles or triangular arbitrage cycles, and you just stop the script. But if there are results, you just ramp them up in a data frame, sort them by the profit percentage, ascending false, so you're getting the best ones first, and then you're just pulling the top 5. Now, if you would run the script, now it's getting interesting, you will get the results as of exactly now, right? So if I'm running this, so this script is called arbitrage2.py. If I'm running this, I'm getting some feedback defined in the prints above, and then after some seconds, I'm getting that the best arbitrage cycle is non-profitable. That would be USDT, BRL, BTC, USDT. This is non-profitable, but this is an interesting one because this would have been profitable without taking fees into account. Because, as I said, you need to account for the fees 3 times. So you could actually test that. How does it look like without fees? So let's say you trade assets with less fees or with 0 fees. How would that look like? You could play a bit around with that and run the script again. And then you're actually getting a slightly positive profit here. And that would even be very slightly positive after subtracting fees, right? So this is obviously changing every single millisecond here, right? So to really analyze those cycles over a long time, you would need to run this over 1 day, over 1 week, over 1 month, and see if there are actually possibilities and if your script could be fast enough to capture those possibilities. So that is something you would need to test out. So I hope you found this video interesting and it made sense to you. If not, let me know in the comments below. And I thank you very much for watching and looking forward to seeing the upcoming videos. Cheers. Bye bye.